Hello there, and welcome back to the Science Sleepy Minds. Tonight, you're standing at the edge of everything you have ever known, toes curled over the lip of a cliff that drops not into water, not into darkness, but into a silence so vast that every sound humanity has ever produced would vanish inside it like a whisper lost in a hurricane. Somewhere out there, roughly 1 billion light years from the pillow your head is resting on right now, there is a galaxy so absurdly, almost offensively large that if you could somehow fly toward it at the speed of light, 300,000 kilometers every single second, you would die of old age, and so would your children, and their children, and roughly 60,000 generations after them, before you even crossed from one side to the other. You probably will not survive this episode emotionally intact, and that is perfectly fine. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Drop a comment telling me where you're listening from and what time it is where you are. I always love reading those. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're lying in bed, and the ceiling above you is doing that thing where it slowly stops being a ceiling and starts becoming a window. The plaster dissolves, the light fixture fades, and suddenly you're looking straight up into a sky so crowded with stars it looks like someone took a handful of powdered sugar and threw it across black velvet. You've seen photographs of the Milky Way, those long exposure shots where the galactic core blazes like a brushstroke of amber and violet, and you have probably thought to yourself, well, that is pretty enormous. 100,000 light years across, 200 billion stars, maybe 400 billion if you count the dim ones hiding in the corners. Our galaxy is, by any human standard, an incomprehensible object. If you drove a car at highway speed, non-stop, no bathroom breaks, no fuel stops, no existential crises at gas stations, it would take you roughly 110 billion years just to cross it. The universe itself is only about 13.8 billion years old, so you would need roughly 8 universe lifetimes of continuous driving. And yet tonight, you're going to discover that the Milky Way is a rounding error, a postage stamp on the wall of a cathedral, a grain of salt sitting on the rim of a dinner plate the size of a football field. The galaxy you're about to meet is called C1101, and it is, by most measurements, the single largest galaxy humanity has ever confirmed. The name sounds clinical, almost boring. Just 2 letters and 4 numbers, the kind of label you might stick on a file folder in an accountant's office. But behind that sterile designation sits an object so enormous that the first time astronomers calculated its true diameter, several of them reportedly went quiet for a long time. Historians of science still argue whether the initial silence in the room was awe or simple disbelief. AC1101 stretches somewhere between 4 and 6 million light years from edge to edge, depending on which measurement you trust and how generously you define edge. For context, that means you could line up roughly 50 to 60 Milky Ways in a row, end to end, and they still might not span the full width of this thing. It contains, by conservative estimates, around 100 trillion stars, not billion, trillion. That is a one followed by 14 zeros, a number so large that if you counted 1 star per second 24 hours a day, you would need about 3.2 million years to finish, and by then several of those stars would have already died and been replaced by new ones. Here is a quirky little aside to tuck under your pillow. When the ancient Greeks looked up at the hazy band of light crossing their night sky, they called it Galaxias Kyklos, the Milky Circle, because they thought the goddess Hera had spilled breast milk across the heavens while nursing Heracles. That mythological spill gave us the word galaxy. Every time an astronomer publishes a paper about galactic mergers and dark matter halos, they are technically writing about spilled divine milk. There is something wonderfully absurd about that, and you're welcome to smile about it as you sink a little deeper into your blankets. But IC1101 is not some gentle splash of milk. It is the entire dairy farm, the surrounding countryside, and a good portion of the neighbouring continent. It sits at the exact gravitational centre of a galaxy cluster called Abel 2029, a cosmic city of thousands of galaxies all bound together by gravity, all slowly spiralling inward like leaves circling a drain. And IC1101 is the drain. It has been sitting there for billions of years, patiently pulling smaller galaxies toward itself, absorbing them, digesting their stars and gas and dust, growing larger and larger and larger until it became something that does not really have an adequate comparison in everyday life. Scholars still debate whether IC1101 reached its current size primarily through steady gravitational accretion, or through a series of catastrophic major mergers, each one a collision between galaxies that were themselves enormous. The answer is probably both, but the exact ratio keeps astrophysicists awake at night, which is ironic, given that you're trying to fall asleep. And here is the thing that might genuinely unsettle you, in the most delicious bedtime story way possible. IC1101 is not just big. It is big enough that light itself, the fastest thing the laws of physics allow, becomes a tortoise inside it. A beam of light leaving one edge of IC1101 would not reach the other side for roughly 6 million years. To put that in perspective, 6 million years ago on Earth, our ancestors were just beginning to walk upright on the African savannah, still figuring out that rocks could be tools. An entire chapter of human evolution could begin and end in the time it takes a photon to commute across this single galaxy. The 17th century astronomer Giovanni Cassini, famous for spotting the gap in Saturn's rings, once mused that the heavens must contain objects beyond human comprehension. He had no idea just how right he was. But if he were alive today and someone showed him the data on IC1101, there is a very real chance he would simply sit down on the floor and refuse to get up. So close your eyes if they're not already closed, and let the numbers wash over you like warm water. You do not need to memorize anything. You do not need to take notes. You just need to let yourself drift into the sheer, terrifying, beautiful scale of the largest galaxy anyone has ever found, and trust that by the time you reach the end of this story, the universe will feel just a little bit bigger than it did when you pressed play. You know how sometimes you learn a word you've used your entire life, and then discover it means something completely different from what you assumed? Galaxy is one of those words. You say it casually. There are billions of galaxies in the universe. The way you might say, there are a lot of fish in the sea, and the statement just floats past without really detonating in your brain. So let us slow down for a moment. Pull the blankets up to your chin, and actually think about what a galaxy is, because you need that foundation before IC1101 can properly terrify you. A galaxy, at its most basic, is a gravitationally bound system of stars, stellar remnants, interstellar gas, dust, and dark matter. Think of it as a cosmic island. Picture the universe as an impossibly vast ocean of almost perfect emptiness, just vacuum and silence stretching in every direction. And floating in that ocean are islands of matter, each one containing millions, billions, or even trillions of stars, all held together by gravity the way a handful of wet sand holds its shape when you squeeze it. Some of these islands are small and ragged, irregular little patches with no real structure, like someone crumpled a piece of tinfoil and tossed it into the void. Others are elegant and symmetrical, spirals with sweeping arms that pinwheel slowly over hundreds of millions of years. And then there are the ellipticals, the big blobby ones shaped like footballs or eggs, with no discernible structure at all. just smooth gradients of ancient starlight fading from a bright core to a dim outer haze. The philosopher Immanuel Kant, back in 1755, proposed something genuinely radical for his time. He suggested that some of the faint fuzzy patches of light visible through telescopes might not be clouds of gas within our own Milky Way, but rather entirely separate island universes, each one a vast collection of stars impossibly far away. Most of the scientific establishment politely ignored him, because in the 18th century you did not get taken seriously when you suggested the universe was that big. It would take almost 200 years before anyone could prove he was right. That proof came in 1924 when Edwin Hubble, yes, the telescope is named after him, and no, he did not personally float in space to look through it, used the Hooker telescope at Mount Wilson Observatory to identify individual Cepheid variable stars in the Andromeda Nebula. Those stars allowed him to calculate a distance so great that Andromeda could not possibly be inside the Milky Way. It had to be its own galaxy, its own island, separated from ours by a gulf of empty space roughly 2.5 million light-years wide. In one elegant observation, the universe got a lot bigger and humanity got a lot smaller. Here is a fringe tidbit that might make you smile in the dark. Before Hubble's discovery, the scientific community held what is now called the Great Debate of 1920, a formal public argument between astronomers Harlow Shapley and Heber Curtis over whether the Milky Way was the entire universe or just one galaxy among many. Shapley insisted everything was contained within our galaxy. Curtis argued for island universes. The debate was held at the Smithsonian, and by all accounts it was politely vicious in the way only academics can manage. No raised voices, just devastatingly precise passive aggression delivered over a podium. Historians still argue whether Shapley genuinely believed his position or was simply defending the model that had built his career. Either way, Curtis turned out to be closer to the truth, and within a few years the question was settled by Hubble's observations. But imagine being Shapley in that moment. You spent your career mapping what you believed was the entire cosmos, and then some guy with a big telescope casually informs you that your entire cosmos is just one neighborhood in an unimaginably larger city. Now, you might be wondering how many of these galactic islands are out there. The honest answer is that nobody knows for certain. Estimates have shifted dramatically over the past few decades. For a long time, the commonly cited number was around 200 billion galaxies in the observable universe. Then, in 2016, a team using data from the Hubble Space Telescope published a paper suggesting the real number might be closer to 2 trillion, 10 times higher than previously thought. Scientists still debate this figure because counting galaxies is not like counting coins in a jar. Many galaxies are too small, too faint, or too far away to detect with current instruments, so every estimate involves extrapolation, statistical modelling, and a generous helping of educated guessing. It is one of those situations where the error bars are almost as interesting as the central estimate. What matters for tonight, though, is not the total number. What matters is that galaxies come in wildly different sizes, and the range is staggering. At the small end you have dwarf galaxies like Segway 2, a pathetic little clump of about 1,000 stars. Barely a galaxy at all, more like a star cluster with aspirations. At the other end you have IC 1101, which could contain 100 trillion stars and stretch across a volume of space so large that most other galaxies could fit inside it, the way a marble fits inside a gymnasium. Between those two extremes lies every galaxy humanity has ever observed, each one a unique gravitational sculpture shaped by billions of years of mergers, collisions, gas flows, and the invisible hand of dark matter. No two galaxies are exactly alike. just as no two snowflakes are exactly alike, except that each of these snowflakes weighs trillions of times more than the sun, and spans distances that light itself struggles to cross in any reasonable time frame. The analogy breaks down rather quickly, but you get the idea. And this is the quiet, slightly unsettling thought you can carry into the next part of this journey. Every galaxy you've ever seen in a photograph, every spiral arm and glowing nebula and dramatic collision captured by Hubble or James Webb, all of it is just the scenery on the road to IC 1101. The real destination is still ahead, and it is larger than anything the road has prepared you for. Let your breathing slow, let your shoulders drop another centimetre into the mattress. You're exactly where you need to be. Picture your home, not your house or apartment, your real home, the one you did not choose, the one you were born into without filling out any paperwork, the Milky Way galaxy. You have been living inside it your entire life, and so has every human who ever existed, and every dinosaur before them, and every single-celled organism that once floated in a warm Precambrian ocean before that. Nothing alive on Earth has ever left this galaxy. Nothing built by human hands has even come close. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object from Earth, and after nearly 5 decades of continuous travel at roughly 60,000 kilometers per hour, it has covered about 24 billion kilometers. That sounds impressive until you realize that the Milky Way is approximately 950,000 trillion kilometers across. Voyager has crossed roughly 0.0000003% of the galaxy. If the Milky Way were the distance from New York to Los Angeles, Voyager would have moved about the width of a credit card. You're not going anywhere, and frankly, neither is Voyager. And the sooner you make peace with that, the more comfortable this pillow is going to feel. The Milky Way is a barred spiral galaxy, which means it has a central bar-shaped structure made of stars, with spiral arms winding outward from the ends of that bar like cream slowly stirring into coffee. There are at least 4 major spiral arms: Perseus, Sagittarius, Scutum Centaurus, and the outer arm, along with several smaller spurs and branches. Our solar system sits on one of these minor spurs called the Orion Spur, roughly 26,000 light-years from the galactic centre. That puts you about halfway between the core and the outer edge, in what astronomers sometimes call the galactic habitable zone, not too close to the radiation-drenched centre, not too far out in the sparse, metal-poor suburbs. It is a remarkably pleasant cosmic address, like living in a quiet cul-de-sac in the middle of a vast, dangerous city. The total mass of the Milky Way is estimated at roughly 1.5 trillion solar masses. The most of that, about 90%, is dark matter, the invisible substance you will learn more about later. The visible part, the stars and gas and dust you can actually see through a telescope, accounts for a surprisingly modest fraction of the total. Our galaxy contains roughly 200 to 400 billion stars, depending on how you count the dim ones, and a significant amount of interstellar gas, mostly hydrogen and helium, swirling through the spiral arms, collapsing into new stars being blown back out by supernovae, and collapsing again in a cycle of creation and destruction that has been running for over 13 billion years. The Milky Way is old. It formed within the first billion years after the Big Bang, and it has been evolving, merging with smaller galaxies, rearranging its arms and slowly growing ever since. By human standards, it is ancient beyond comprehension. By the standards of IC 1101, it is a modest structure that barely registers on the cosmic leaderboard. But you live here, and that makes it the most important galaxy in your personal universe, and there is nothing wrong with being sentimental about your own address. At the very centre of the Milky Way, hidden behind thick clouds of gas and dust that block visible light, sits a supermassive black hole called Sagittarius A star. It has a mass of about 4 million suns, enormous by any earthly standard, but you will soon learn that IC1101's black hole makes Sagittarius A star look like a bath plug next to a whirlpool. Sagittarius A star was first detected in 1974 by astronomers Bruce Balick and Robert Brown, who noticed an unusually compact radio source coming from the direction of the galactic centre. It took decades of painstaking observation, including tracking individual stars as they orbited the invisible mass, before the scientific community fully accepted that a supermassive black hole was sitting at the heart of our galaxy. Andrea Ghez and Reinhard Genzel shared the Nobel Prize in Physics in 2020 for that work, and it remains one of the most elegant pieces of observational astronomy ever conducted. Here is a quirky detail that might lodge itself pleasantly in your brain. The Milky Way is currently on a collision course with the Andromeda Galaxy, our nearest large galactic neighbour, and the two are expected to merge in roughly 4 to 5 billion years. Astronomers have already given the future merged galaxy a name, Milkomeda. Some prefer Milkdromeda. Researchers still debate which name will ultimately stick, and honestly, the fact that scientists are arguing about the branding of an event that will not happen for 4 billion years is one of the most endearing things about the human species. When the merger does happen, it will be extraordinarily slow by human standards. The two galaxies will dance around each other for billions of years, their spiral arms stretching and distorting, stars flung into new orbits, gas clouds compressed into bursts of new star formation. But here is the beautiful part. Despite the galaxies containing hundreds of billions of stars between them, the chances of any two individual stars actually colliding are essentially zero. Stars are so far apart relative to their size that the galaxies will pass through each other like two swarms of bees merging in a meadow. Chaotic, but surprisingly non-violent at the individual level. But Milkomeda, as grand as it will still be a middleweight. Even after the Milky Way and Andromeda combine their stars, their gas, their dark matter halos, the resulting galaxy will still be a fraction of the size of IC1101. You could take Milkomeda, this future mega-galaxy born from the most dramatic event in our local cosmic neighbourhood, and tuck it into a corner of IC1101 where it would barely register. It would be like dropping a tennis ball into an Olympic swimming pool and asking people to find it. The scale difference is not merely large, it is the kind of large that makes your brain quietly refuse to process the information, the way your computer freezes when you ask it to open a file that is far too big. And your brain, wonderfully, is starting to do that gentle freeze right now, not in a stressful way, but in the warm, heavy, syrupy way that means sleep is beginning to circle your thoughts like a cat settling into a lap. Let it circle. You are safe here. The Milky Way may be small, but it is yours, and its 100 billion stars are keeping you company tonight. Not all galaxies are built the same, and understanding why is going to matter enormously when you finally stand face to face with IC1101 and try to comprehend how something that shape and that size can even exist. So settle in, because you are about to get a quiet little tour of galactic taxonomy, and it is going to be more interesting than it sounds, sort of like how a documentary about deep-sea fish always ends up being surprisingly riveting, even though you clicked on it by accident. In 1926, Edwin Hubble, the same man who proved galaxies existed beyond the Milky Way, proposed a classification system that astronomers still use in modified form today. He organised galaxies into a diagram shaped like a tuning fork, which is why it is called the Hubble tuning fork. On one prong, You have spiral galaxies, subdivided into normal spirals and barred spirals, depending on whether they have a bar-shaped structure running through their centre. These are the photogenic ones, the galaxies that end up on posters and desktop wallpapers, sweeping arms of blue-white young stars, lanes of dark dust, glowing pink nebulae where new stars are being born. The Milky Way is a barred spiral, so is Andromeda, more or less. They are dynamic, active, messy with creation. On the other prong sit the elliptical galaxies, and these are a completely different animal. Ellipticals range from nearly spherical to elongated like a rugby ball, and they're classified on a scale from E0, which is almost perfectly round, to E7, which is the most elongated. Unlike spirals, ellipticals have very little interstellar gas and dust. They have almost no ongoing star formation. They are populated predominantly by old red, low-mass stars that have been burning slowly for billions of years, like embers in a fireplace that stopped receiving fresh logs a very long time ago. Ellipticals tend to look smooth and featureless in photographs. No dramatic arms, no vivid nebulae, just a soft, uniform glow that fades from bright centre to dim edge. They are, in a word, quiet, but do not mistake quiet for small. Here's where things get interesting and slightly ominous. The very largest galaxies in the universe are almost always elliptical, and the reason for that is violence. Elliptical galaxies are thought to form primarily through mergers. When two large spiral galaxies collide and merge, a process that takes billions of years, the organised rotation of their spiral arms gets disrupted, stars are flung into random orbits, and what remains is a bloated, disorganised elliptical galaxy, with stars moving in every direction like a swarm of confused bees. Every major merger makes the resulting elliptical bigger, and if that elliptical happens to sit at the centre of a galaxy cluster, where the gravitational well is deepest and smaller galaxies are constantly falling inward, the mergers never stop. The elliptical just keeps eating. Astronomers call this process galactic cannibalism, and it is exactly as dramatic as it sounds, though considerably slower, unfolding over timescales that make geological time look like a microwave timer. There is a special subclass of elliptical galaxy that sits at the extreme end of this spectrum, and it is called a CD galaxy. The C stands for supergiant, because apparently even astronomers occasionally feel the need to be dramatic, and the D indicates a diffuse stellar envelope, meaning the galaxy has a vast, faintly glowing halo of stars extending far beyond its bright central region. A CD galaxy is what happens when an elliptical galaxy at the centre of a cluster has been cannibalising its neighbours for so long that it has accumulated an absurd surplus of stars, creating an extended outer envelope that can stretch for millions of light years. They are the apex predators of the galactic food chain, the blue whales of the cosmos, except a blue whale eventually stops growing, and a CD galaxy, in theory, does not, at least not until it runs out of things to eat. The stellar envelopes of CD galaxies can extend so far from the core that they overlap with the light of the surrounding cluster itself, and disentangling which stars belong to the galaxy and which belong to the cluster's general background is one of the recurring headaches of extragalactic astronomy. It is a boundary problem in the most literal sense. Where does the galaxy end and the universe begin? And for the largest CD galaxies, the honest answer might be nowhere. They simply fade asymptotically into everything else. IC1101 is a CD galaxy. Of course it is. It is the biggest, the most extreme, the most gluttonous example of this already extreme category. It sits at the gravitational centre of the Abel 2029 galaxy cluster and has been accumulating mass for billions upon billions of years. researchers still argue about the exact formation history, whether IC1101 grew primarily through many small mergers or through a smaller number of truly colossal collisions between galaxies that were themselves enormous. The evidence suggests a mix of both, but the details remain one of the open questions in extragalactic astronomy, the kind of question that generates lengthy papers with titles no normal human would ever read voluntarily. Here is a quirky tidbit to take with you. The Hubble tuning fork diagram, elegant as it is, was originally intended not just as a classification tool, but as an evolutionary sequence. Hubble initially believed that galaxies evolved from ellipticals into spirals over time, that ellipticals were early type galaxies and spirals were late type. This turned out to be completely wrong. If anything, the evolution tends to go in the opposite direction, with spirals merging to form ellipticals. But the terminology stuck, and to this day astronomers still refer to ellipticals as early type and spirals as late type, even though everyone knows the labels are backward. It is one of those charming little fossils of scientific history, like how we still call them tin cans, even though they have not been made of tin in over a century. Science, like language, accumulates scar tissue from its own past mistakes, and sometimes it just learns to live with it. You're doing beautifully, by the way. Your breathing has probably slowed a little. The facts are settling into your mind like snowflakes landing on warm ground, present for a moment, then absorbed, leaving just a faint impression of cold. You've been drifting through the idea of galaxies as islands, and now it's time to zoom out even further, because galaxies do not live alone. They cluster, they gather, they form communities bound by gravity, and these communities have a name that sounds deceptively simple: galaxy clusters. If galaxies are houses, then galaxy clusters are cities, vast metropolitan regions where hundreds or thousands of galaxies orbit a common centre of mass, all of them tugged and pulled and jostled by the collective gravity of everything around them. And just like real cities, galaxy clusters have a downtown, a dense core where the biggest, wealthiest, most dominant structure sits. In the case of the galaxy cluster you're about to visit, that dominant structure is IC1101, and it has been running its city for a very long time. Galaxy clusters are the largest gravitationally bound structures in the universe, and if that phrase does not immediately make your pulse quicken, let me unpack it, because it is more dramatic than it sounds. That phrase, gravitationally bound, is important because it means these objects are held together by gravity despite the expansion of the universe trying to pull everything apart. Larger structures exist, like superclusters and cosmic filaments, but those are not truly bound. They are more like loose associations, neighbourhoods that happen to be near each other but are slowly being separated by the expanding fabric of space-time. Galaxy clusters, by contrast, are locked in. Their galaxies orbit their common centre, the way planets orbit a star, just on a vastly larger and slower scale. A single orbit within a large galaxy cluster can take billions of years, which means some of the galaxies in these clusters have only completed a handful of orbits since the universe began. The space between galaxies inside a cluster is not empty, and this is one of those facts that catches people off guard. That intergalactic space is filled with an extremely hot, extremely diffuse gas called the intracluster medium. This gas can reach temperatures of tens of millions of degrees, far hotter than the surface of any star, and it emits X-rays so powerful that space-based X-ray telescopes like Chandra can detect them from billions of light-years away. The mass of this hot gas often exceeds the total mass of all the stars in all the galaxies in the cluster combined, sometimes by a factor of 5 or more, a fact that continues to astonish even experienced astronomers who should, by now, be used to the universe hiding most of its contents in the least obvious places, you read that correctly. There is more stuff between the galaxies than inside them. It's as if you discovered that the air in a city weighed more than all the buildings, cars and people put together. The intra-cluster medium is one of those cosmic details that makes you realize how much of the universe is hidden in the gaps between the things you can actually see. Now, let me introduce you to the specific cluster where our monster lives, Abel 2029. It is named after George Abel, an American astronomer who in 1958 published a landmark catalogue of galaxy clusters using photographic plates from the Palomar Observatory Sky Survey. Abel spent years hunched over these plates with a magnifying loupe, manually identifying clusters of galaxies by their visual appearance, a painstaking process that required both extraordinary patience and a very strong back. His catalogue listed 2,712 clusters, each one assigned a simple number. Cluster number 2029 happened to contain one of the most remarkable objects in the observable universe, but at the time, Abel had no way of knowing that. He was just cataloguing smudges on glass plates, sorting the cosmos one photograph at a time. Historians of astronomy still debate whether Abel fully appreciated the significance of some of his entries, or whether the sheer volume of the work made each individual cluster blur into the next. Abel 2029 sits roughly 1 billion light-years from Earth in the direction of the constellation Serpens, the Serpent. It contains thousands of galaxies, all embedded in a massive halo of dark matter and bathed in that blisteringly hot intra-cluster gas. X-ray observations reveal that the gas in Abel 2029 is remarkably smooth and symmetrical, which tells astronomers that this cluster has not experienced a major disturbance in a long time. It is, by cluster standards, relaxed, a settled, mature city that finished its most dramatic construction phase billions of years ago and has since been quietly aging in place. At the very centre of this relaxed cluster, sitting at the exact point where the gravitational potential is deepest, where the dark matter is densest, where the hot gas is brightest in X-rays, sits IC1101. Here is a fringe detail that deserves a moment of your sleepy attention. Some galaxy clusters are so massive that they visibly bend the light passing through them, a phenomenon predicted by Einstein's general theory of relativity called gravitational lensing. The gravity of the cluster warps the fabric of space-time itself, and light from more distant galaxies behind the cluster follows those curves, arriving at our telescopes distorted, stretched into arcs, duplicated into multiple images, sometimes magnified into visibility when they would otherwise be too faint to detect. Abel 2029 is massive enough to produce this effect, and astronomers have used its gravitational lensing to study galaxies that are even farther away, effectively using the cluster as a cosmic magnifying glass. Researchers still argue about the precise mass distribution within Abel 2029, because the lensing data does not always agree perfectly with the X-ray data, and reconciling the two requires assumptions about how dark matter is distributed on scales that are difficult to probe directly. You're now standing at the gates of the city. The cluster sprawls around you in every direction, thousands of galaxies like scattered lanterns, the hot intergalactic gas glowing faintly in wavelengths your eyes cannot see. Dark matter forming an invisible scaffolding that holds everything in place. And there, at the centre, larger than everything else combined, glowing with the ancient light of 100 trillion stars, sits the object you came here to find. IC1101 is waiting for you, and it has been waiting for a very, very long time. Let your eyelids grow just a fraction heavier. The next step takes you inside. The story of how humanity found EC1101 is not a story of a single eureka moment. It is more like the slow development of a photograph in a darkroom, the image emerging gradually, one chemical wash at a time, until what was once a blank white sheet suddenly contains something that makes you take a step back and whisper an expletive under your breath. The galaxy did not announce itself. It was not discovered in a blaze of telescope time and press conferences. It crept into human awareness over decades, and that slow reveal is part of what makes it so unsettling. The name IC1101 tells you where to start. The IC stands for Index Catalogue, a supplement to the older New General Catalogue that was itself a supplement to even older star catalogues stretching back centuries. The Index Catalogue was compiled by John Louis Emile Dreyer, a Danish-Irish astronomer working at Armagh Observatory in Northern Ireland during the late 1800s. Dreyer was not a glamorous figure. He was a cataloguer, a meticulous organiser of other people's observations, the kind of scientist who understood that sometimes the most important work is not making the discovery, but recording it in a place where someone else can find it later. Between 1888 and 1908, Dreyer compiled thousands of entries for nebulae, star clusters and galaxies, though at the time the distinction between a nebula and a galaxy was not yet clear. Entry number 1101 in his index catalogue was a faint, diffuse smudge of light in the direction of the constellation Serpens, observed through telescopes that were powerful for their era, but comically primitive by modern standards. Dreyer noted its position, its approximate brightness, and its fuzzy appearance, and then moved on to entry 1102. He had no fanfare, no eureka moment, no champagne. Just a careful notation in a ledger, another data point in a career built on meticulous record keeping. The tools he worked with would seem almost laughably simple today: handwritten notes, visual estimates of brightness, coordinates calculated by hand. But catalogues endure in a way that headlines do not, and Dreyer's careful entry would eventually lead astronomers to the most astonishing single object in the sky. There was no way for him to know what he had just catalogued. It would be like a 19th century cartographer drawing a small island on a map, not realizing that the island was actually the tip of an underwater mountain taller than Everest. For decades, IC1101 sat in the catalogue as just another faint fuzzy object among thousands. The early 20th century brought revolutions in astronomy: Hubble's discovery of extragalactic distances, the realization that the universe was expanding, the development of radio astronomy. But IC1101 remained in relative obscurity. It was too far away and too faint for the telescopes of the mid-20th century to reveal much about. It was known to be a galaxy, and it was known to be at the centre of a galaxy cluster, but its true scale was not yet apparent. Figuring out the size of a galaxy is harder than you might think. You need to know its distance from Earth with reasonable precision, which requires identifying reliable distance indicators like the brightness of certain types of stars or the redshift of its light. And you need to define where the galaxy ends, which is surprisingly difficult because galaxies do not have hard edges. They fade gradually into the intergalactic background, and where you draw the boundary depends on what instruments you are using and what surface brightness threshold you choose. The breakthrough came in stages during the late 20th century, as telescopes grew larger and more sensitive, and as astronomers developed better techniques for measuring distances and mapping the distribution of light in distant galaxies. Observations in the 1980s and 90s, particularly using CCD detectors that were far more sensitive than the photographic plates of earlier generations, began to reveal that IC1101 was not just a large galaxy, but a spectacularly, anomalously, almost absurdly large galaxy. Its diffuse outer envelope extended far beyond what anyone had expected, stretching to diameters that dwarfed every other galaxy in the catalogues. Published estimates of its size have varied. Some papers cite a diameter of about 4 million light-years, others push it closer to 6 million. And historians of the field still argue about which measurement should be considered the most reliable, since different studies use different methods, different wavelengths of light, and different definitions of where the galaxy's edge lies. That ambiguity is frustrating if you want a single clean number, but it is also honest because the universe does not owe us tidy boundaries. Here is a fringe tidbit worth savouring. Before modern CCD detectors, astronomers measured the brightness of galaxies using a device called a photometer attached to the telescope, which essentially converted light into an electrical signal one painstaking point at a time. Mapping the brightness profile of a single galaxy could take an entire night of observing, and the results were often noisy and uncertain. The astronomers who first attempted to measure IC 1101's extended envelope with these instruments would have seen the brightness curve refuse to drop to zero long after it should have, the signal stubbornly continuing outward and outward like a staircase that never reaches the ground floor. One can imagine the quiet disbelief in the observing room, checking the instrument, recalibrating, checking again, and finally accepting that the galaxy really was that big. The scholarly debate around EC 1101's size continues to this day, and it is worth noting that some more recent analyses have argued for a somewhat smaller diameter than the most dramatic early estimates. Astronomers still argue whether the outermost reaches of IC 1101's stellar envelope should properly be attributed to the galaxy itself or to the intra-cluster light, a diffuse glow of stars that have been stripped from their parent galaxies and now drift freely within the cluster, belonging to no galaxy in particular. This distinction matters because it changes whether I mean C1101 is merely extraordinarily large or incomprehensibly large, and both options are, frankly, terrifying in their own way. You're learning the name of the beast now, IC1101. Say it quietly to yourself if you like. It has a certain clinical rhythm to it, like a medical code for something you would rather not have. But behind those letters and numbers is an object that took humanity centuries to even notice, decades more to measure, and that still resists our attempts to fully define its boundaries. Breathe. Let the history settle. The numbers are coming next, and they are going to be much, much worse. Numbers are about to happen to you now, and there is nothing you can do to stop them. But do not worry. The trick with truly enormous numbers is to stop trying to understand them intellectually, and instead let them wash over you the way a warm wave washes over your feet at the beach. You feel it, you know it is big, and then it recedes, and you're still standing. So here come the numbers for IC1101, and you're going to be fine. Probably. IC1101 has an estimated diameter of somewhere between 4 and 6 million light-years. Let us use a middle estimate of about 5.5 million light-years, understanding that the real answer depends on where you draw the boundary. 5.5 million light-years. That number by itself means almost nothing to a human brain. It is too large to visualize, too abstract to feel. So, let us build some comparisons. The Milky Way, your home galaxy, is about 100,000 light-years across. IC1101 is roughly 50 to 60 times wider. If the Milky Way were a standard dinner plate, about 27 centimeters in diameter, then IC1101 would be a circle roughly 15 meters across. You could set that dinner plate down in the center, and it would look lonely, almost comically small, a white ceramic disc sitting in the middle of a space large enough to host a concert. That is about the size of a decent backyard swimming pool. You're a pattern on the dinner plate trying to imagine the swimming pool. Now stack the comparison differently. If the Milky Way were the size of a 25-cent coin, IC1101 would be roughly the size of a large serving platter at a restaurant. The kind they bring out when someone orders the sharing paella for 6 people and immediately regrets it. Let us try distance instead of size. Light, the fastest thing in the universe, travels at roughly 300,000 kilometers per second. At that speed, light can circle the Earth 7.5 times in a single second. It crosses the distance from Earth to the Moon in about 1.3 seconds. It reaches the Sun in about 8 minutes. It exits the solar system, passing the orbit of Pluto, in about 5.5 hours. To cross the entire Milky Way, light needs 100,000 years. To cross IC1101, light needs somewhere between 4 and 6 million years. Let that soak in for a moment. A beam of light that left one side of IC1101 when our earliest hominid ancestors were still figuring out how to chip rocks into tools would not yet have reached the other side. The entire duration of human evolution, from the first bipedal apes on the African savanna to you lying here in your bed listening to this, fits comfortably inside the time it takes a photon to commute across this one single galaxy. And a photon does not stop for coffee. In terms of volume, the difference is even more staggering. Volume scales with the cube of the diameter, so if IC1101 is 55 times wider than the Milky Way, its volume is roughly 55 cubed, about 166,000 times greater. That means you could theoretically fit over 160,000 Milky Way-sized galaxies inside the volume of IC1101. 160,000. That is roughly the population of a mid-sized city, except instead of people you are counting entire galaxies, each one containing hundreds of billions of stars, each star potentially hosting its own system of planets, moons, and asteroids. The number is so large that it starts to feel like a prank, like the universe is messing with you specifically. And you know what? Maybe it is. Here's a historical fact to anchor all of this in something human. In 1610, Galileo Galilei pointed his homemade telescope at the Milky Way and discovered that the faint smear of light was actually composed of countless individual stars too faint to see with the naked eye. This was a genuine revelation. Before Galileo, nobody knew what the Milky Way was made of. He published his findings in a slim book called Sidereus Nuncius, the Starry Messenger, and it changed astronomy forever. But Galileo's telescope had a magnification of about 20 times. The telescopes used to study IC1101 have effective magnifications millions of times greater, and they are looking at an object roughly 10,000 times wider than anything Galileo could have imagined. If you could somehow show Galileo the data on IC1101, the diameter, the star count, the mass, there is a very real chance his brain would simply reject the information as a fever dream. Scholars still debate how Galileo would have reacted to the scale of the modern universe, since his own writings suggest he believed the cosmos was large but not infinite. IC1101 would have tested that belief rather severely. And here is a quirky little fringe detail. Some astronomers have attempted to calculate what IC1101 would look like if it were placed at the distance of the Andromeda Galaxy, about 2.5 million light-years away. Andromeda, when you see it with the naked eye from a dark location, appears as a faint fuzzy smudge about 6 times the width of the full moon. IC1101 at the same distance would span a significant portion of the sky. Some estimates suggest it could appear dozens of times wider than the moon, a vast diffuse glow covering a huge patch of sky, turning every moonless night into something resembling a warm perpetual twilight. You would not need a telescope. You would not even need good eyesight. It would be the most prominent feature of the night sky, a soft, omnipresent glow that would have shaped human mythology navigation, religion, and art from the very beginning of civilization. But it's not at Andromeda's distance. It is 1 billion light-years away, hiding in the deep, and you can only see it by building machines that took centuries of cumulative engineering to create. Let your jaw unclench. Let the numbers blur. They have done their job. 100 trillion stars. That is the estimated population of EC 1101, and you're now going to spend a few minutes letting that number crawl under your skin, because it deserves more than a quick mention. 100 trillion. Written out, it looks like this. 100 trillion. 14 digits, a 1 followed by 14 zeros. Humanity uses numbers like this occasionally, in discussions of national debt, in counting the cells in a human body, in calculating the distance to faraway objects in centimetres for no practical reason. But we never truly feel them. Your brain was not designed to feel numbers this large. It was designed to count the berries on a bush and track the members of your tribe, and it maxes out at roughly a few thousand before everything blurs into a lot. So let us find some bridges between the number you can feel and the number IC 1101 demands. Start with grains of sand. There are roughly 7.5 quadrillion grains of sand on all of Earth's beaches combined. That is a 7 followed by 18 zeros. 100 trillion is only about 1.3% of that number, so if you scooped up about 1% of all the sand on every beach on Earth, you would have approximately 1 grain for every star in IC 1101. That is still an insane amount of sand, but it is a useful mental image. Imagine a few very large dump trucks full of sand and every single grain is a star, most of them larger than our Sun, each one with its own story of formation, fusion, and eventual death. Some of those grains are ancient red dwarfs that have been burning since before the Earth existed. Others are bloated red giants in the final stages of their lives, their outer layers puffing outward like a slow exhalation. And scattered among them, rare but spectacular, are the remnants of stars that have already died. White dwarfs, neutron stars, black holes, each one a tombstone marking the end of a stellar life that lasted millions or billions of years. Now try time. 100 trillion seconds is roughly 3.2 million years. That sounds almost manageable until you realise it means that if you had started counting IC 1101 stars at a rate of 1 per second, the moment the first members of the genus Homo appeared on the African continent, you would just now be finishing the count. Every second of every minute of every hour of every day for 3.2 million years, and you would have counted each star exactly once. If you lost count at any point, sneezed, blinked too long, fell asleep the way you're thinking about doing right now, you would have to start over. The entire exercise is a monument to absurdity, which is precisely the point. Human heartbeats offer another way in. The average human heart beats about 100,000 times per day, or roughly 2.5 billion times in a 70-year lifetime. To reach 100 trillion heartbeats, you would need 40,000 human lifetimes. Not 40,000 heartbeats, 40,000 entire lives, each one lived from birth to death, every beat counted. Line those lives up, end to end, and you cover roughly 2.8 million years of continuous human existence, all to match the number of stars in a single galaxy that most people have never heard of. Here is a mainstream historical fact to keep things grounded. In the early 1920s, when astronomers were first beginning to understand that galaxies were separate from the Milky Way, the estimated number of stars in our own galaxy was much smaller than current figures suggest. Some early estimates put it at around a few billion. The idea that a galaxy could contain hundreds of billions of stars, let alone 100 trillion, would have been considered outlandish. Jacobus Kapteyn, a Dutch astronomer who created one of the first modern models of the Milky Way in 1922, estimated our galaxy's diameter at roughly 55,000 light-years, about half its actual size, and his star count was correspondingly modest. Science has a long tradition of underestimating the universe, and IC1101 is perhaps the most extreme example of how the cosmos keeps exceeding our most generous projections, a quirky detail worth preserving in your fading consciousness. Not all of IC1101's 100 trillion stars are created equal. The vast majority are small, dim, red dwarf stars, stellar lightweights that burn their hydrogen fuel so slowly they can last for trillions of years, far longer than the current age of the universe. These little stars are the background hum of IC1101, the countless quiet embers that make up most of its population but contribute relatively little to its total brightness. The luminosity of the galaxy is dominated by a much smaller number of brighter stars, red giants, supergiants, and whatever blue stragglers remain from ancient encounters where two older stars merged and briefly masqueraded as a younger, hotter star. Blue stragglers are the cosmological equivalent of someone at a retirement home who insists on doing backflips. Technically possible, mildly concerning, and a reminder that the universe does not always follow the expected script. Researchers still debate the exact stellar population of IC1101, and the 100 trillion figure is an estimate based on the galaxy's total luminosity and assumed mass-to-light ratio. Different assumptions yield different numbers, and some models suggest the true count could be somewhat lower, perhaps 50 to 80 trillion, while others argue it could be even higher if the faint outer envelope contains a larger than expected population of dim stars. The uncertainty is a reminder that even for the most studied objects in the sky, our knowledge is built on layers of inference, each layer resting on assumptions that are themselves subject to revision. But whether the true number is 50 trillion or 150 trillion, the conclusion is the same. IC1101 contains more stars than you could count in any number of lifetimes, and every single one of them is a nuclear furnace converting hydrogen into light, heat, and heavier elements through the same fundamental physics that powers your own sun. You share something with those stars, even at a distance of 1 billion light-years. You're made of the same stuff, obeying the same laws, slowly burning through your own fuel in your own way. Let that thought be a blanket. Pull it over yourself and keep going. At the centre of every large galaxy, like the pit at the centre of a peach, sits a supermassive black hole. This is not a maybe or a sometimes. It appears to be a universal rule, one of those patterns that nature insists on repeating everywhere we look. The Milky Way has Sagittarius A star, a black hole with a mass of about 4 million suns. Andromeda has one estimated at roughly 100 million solar masses. The galaxy M87, made famous in 2019 when the Event Horizon Telescope captured the first ever image of a black hole's shadow, has a central monster weighing in at about 6.5 billion solar masses. These are formidable objects, engines of destruction that warp space and time so severely that nothing, not even light, can escape once it crosses the event horizon. But IC1101's black hole makes all of them look modest. Estimates for the mass of IC1101's central supermassive black hole range from about 40 billion to 100 billion solar masses. Let us sit with that for a moment. 100 billion times the mass of the Sun. The Sun, by the way, is already a staggeringly massive object. It contains 99.8% of all the mass in the entire solar system, and you could fit 1.3 million Earths inside it. Multiply that mass by 100 billion and you get an object so dense, so gravitationally overwhelming, that the math describing it bends into shapes that make physicists quietly uncomfortable. To grasp that number, consider this. If you replace the Sun with this black hole, its gravitational influence would extend so far that the orbits of the planets would be meaningless. Not because the planets would be sucked in immediately, but because the sheer scale of the event horizon would engulf them before they had a chance to orbit anything. If this black hole's event horizon were a sphere, and at this scale it would be very close to spherical, its diameter could be roughly 600 billion kilometers. That is larger than our entire solar system. The event horizon alone, the point of no return, would swallow the Sun, all 8 planets, the asteroid belt, the Kuiper belt, and still have room left over for a few extra Plutos, which would at least give Pluto something to feel smug about after being demoted from planet status in 2006. Here is a mainstream historical fact to keep your eyes closed and your mind gently occupied. The concept of a dark star, an object so massive that even light could not escape its gravitational pull, was first proposed in 1783 by John Michell, an English clergyman and natural philosopher who was one of the most underappreciated scientists in history. Michell reasoned that if a star were massive enough and dense enough, its escape velocity would exceed the speed of light, rendering it invisible. He even calculated roughly how large such an object would need to be. This was over a century before Einstein's general theory of relativity provided the proper mathematical framework for black holes, and yet Michell's intuition was remarkably close to the mark. He also invented the torsion balance, contributed to the study of earthquakes, and was friends with Henry Cavendish, who used Michell's equipment to weigh the Earth. If scientific fame were distributed fairly, Michell would be a household name, but history has a habit of forgetting the people who were right too early. The black hole at the centre of EC 1101 did not form all at once. Supermassive black holes are thought to grow through a combination of direct accretion, gas and dust falling inward and adding mass, and mergers with other black holes. When 2 galaxies collide and merge, their central black holes eventually spiral toward each other and coalesce into a single, larger black hole, a process that releases gravitational waves powerful enough to ripple the fabric of space-time across the cosmos. IC 1101, having consumed hundreds or thousands of smaller galaxies over its lifetime, would have accumulated the black holes from each of those mergers, each one adding to the mass at the centre like coins dropping into a piggy bank that never gets full. Researchers still argue about the relative importance of accretion versus mergers in building the most massive black holes, and the answer likely varies from galaxy to galaxy. For IC 1101, the sheer number of past mergers suggests that black hole coalescence played a significant role, but direct accretion during active galactic nucleus phases, periods when the black hole was actively devouring surrounding material and blazing with the luminosity of an entire galaxy, would have contributed as well. Here is a quirky, slightly unnerving fringe tidbit. Some theoretical models suggest that the most massive supermassive black holes might approach a practical upper limit, beyond which they can no longer grow efficiently. The idea is that once a black hole becomes massive enough, the radiation from infalling material becomes so intense that it actually pushes away the surrounding gas, choking off the food supply in a cosmic version of being too full to eat another bite. This theoretical limit is sometimes called the black hole mass ceiling, and estimates place it somewhere around 50 to 100 billion solar masses. If IC 1101's black hole is indeed near the upper end of its estimated range, it may be bumping up against this ceiling, one of the most massive black holes that physics allows to exist. Scholars still debate whether this ceiling is truly firm or whether exotic feeding mechanisms could push black holes beyond it. But the possibility that IC1101 harbours a black hole near the theoretical maximum is one of those facts that makes you feel very small and very temporary, which is, coincidentally, exactly the right feeling for falling asleep. The black hole is silent now, by the way. IC1101's central engine appears to be in a quiescent state, no longer actively devouring large quantities of material. There are no jets, no blazing accretion disks, no torrents of X-rays screaming from the core, just a vast, patient gravitational silence, like a predator that has finished eating and is now resting with its eyes half closed, digesting the remains of 1 billion years of meals. The feast is over for now, but the mass remains sitting there in the dark at the core of the largest galaxy ever found, warping space-time into a funnel so deep that nothing has ever climbed back out of it, or ever will. Pleasant dreams. You have heard the word cannibalism used in polite astronomical conversation, and now it is time to lean into it, because the way IC1101 achieved its size is frankly one of the most brutally elegant stories in all of astrophysics. This galaxy did not grow by being creative or innovative, it grew by eating. Specifically, it grew by eating other galaxies, dozens of them, hundreds of them, possibly thousands, over a span of billions of years. It is the cosmic equivalent of a restaurant owner who stays in business not by improving the menu, but by buying out every other restaurant on the street and absorbing their kitchens, their staff, and their customers. It is a strategy that lacks subtlety but delivers results, and IC1101 is the result. The process is called hierarchical structure formation, and it is one of the central ideas in modern cosmology. The universe did not start with giant galaxies. It started with tiny fluctuations in the density of matter, small regions where there was slightly more stuff than average, and other regions where there was slightly less. Gravity, being the patient and relentless force that it is, slowly amplified these fluctuations. The denser regions pulled in more matter, grew denser still, and eventually collapsed into the first small structures, dark matter halos, gas clouds, proto-galaxies. These small structures then merged with each other, forming larger structures, which merged with still larger structures, in an ongoing chain of cosmic consolidation that continues to this day. Every large galaxy you see in the universe is the product of countless mergers stretching back to the earliest epochs of cosmic history. The Milky Way itself has absorbed numerous smaller galaxies over its lifetime, and the evidence is still visible in the form of stellar streams, thin ribbons of stars that trace the orbits of galaxies the Milky Way tore apart and digested. But IC1101 took this process to an extreme that most galaxies never approach, and the reason is location. Remember Abel 2029, the galaxy cluster where IC1101 sits at the very centre? That central position is not a coincidence, it is the cause. In a galaxy cluster, the gravitational potential well is deepest at the centre. Galaxies that wander too close to the centre lose orbital energy through a process called dynamical friction, essentially gravitational drag caused by interactions with surrounding matter, and slowly spiral inward, like marbles rolling down the inside of a bowl. When they reach the bottom of the bowl, they encounter IC1101, and the encounter does not end well for them. The smaller galaxy is tidally disrupted. Its stars are stripped away by IC1101's immense gravity. Its gas is absorbed, its dark matter halo is assimilated, and whatever remains of its identity is dissolved into the larger galaxy's vast featureless envelope. The process takes hundreds of millions of years per merger, sometimes longer, but IC1101 has had billions of years to work with and an entire cluster's worth of victims to consume. The evidence for this cosmic feeding frenzy is written in IC1101's structure. The enormous diffuse stellar envelope that extends millions of light years from the galaxy's core is thought to consist largely of stars that were stripped from infalling galaxies during these mergers. These stars are on chaotic, random orbits. They're not neatly organised like the stars in a spiral arm, but instead swarm in every direction. The gravitational debris of a billion years of demolition. Some researchers have found faint tidal features, streams and shells of stars at the outskirts of similar CD galaxies that serve as direct evidence of recent meals. It is like finding food crumbs on the face of a very large and very unapologetic eater. Here is a quirky historical detail worth noting. The concept of galaxies consuming other galaxies was first seriously proposed in the 1970s by astronomer Jeremiah Ostraker and colleagues, who argued that the brightest galaxies in clusters grew by galactic cannibalism. The term was deliberately provocative. Ostraker wanted people to pay attention, and it worked. The idea was initially controversial, with some astronomers arguing that CD galaxies could have formed in a single monolithic collapse rather than through mergers. Researchers still debate the relative importance of major mergers versus minor mergers in building the most massive galaxies, and the answer likely involves both processes operating simultaneously at different epochs. A major merger occurs when two galaxies of roughly comparable size collide and produce something dramatically different from either parent. A minor merger is more like a snack, a large galaxy absorbing a much smaller one with minimal disruption to its own structure. IC1101 has almost certainly experienced both, but given the sheer amount of mass it has accumulated, the major mergers would have been the transformative events, the meals that fundamentally changed the galaxy's size and character. Think of it this way: if IC1101 were a snowball, the minor mergers are the individual snowflakes drifting onto its surface, each one adding a tiny bit of mass. The major mergers are the moments when someone rolled another snowball into it, a sudden, dramatic increase in size that reshapes the whole structure. Over billions of years, both processes contribute, and the snowball grows into something that no longer resembles a snowball at all, but rather a small mountain of compressed ice, sitting heavily on the landscape, daring anything else to approach. There is one more detail about galactic cannibalism that might lodge itself in your sleepy brain. When two galaxies merge, their stars almost never collide with each other. Remember, stars are incredibly far apart relative to their size, like grains of sand separated by kilometers of empty space. What does collide is the gas. The interstellar gas from both galaxies smashes together, compresses, heats up, and in many cases triggers enormous bursts of new star formation, stellar baby boom sparked by cosmic violence. But in IC1101's case, most of that gas has long since been used up or heated to temperatures too high for star formation. The mergers now are dry, star-on-star events with no new stars being born, just more mass being added to an already overstuffed galaxy. IC1101 is still eating, but it is no longer cooking. It is merely stockpiling ingredients it will never use, growing larger for the sake of growing larger, a gravitational habit it cannot seem to break. Feel your body settle deeper. The galaxy has eaten its fill, and so has your waking mind. The next stretch is gentler. There is a phrase astronomers use that sounds almost poetic until you realise how bleak it actually is. Red and dead. It describes a galaxy that has stopped forming new stars, one whose remaining stellar population is dominated by old, cool, red stars that are slowly, quietly burning through the last of their hydrogen fuel with no hope of replacement. IC1101 is red and dead. It is the largest red and dead galaxy we have ever found, and the phrase carries a weight that is both scientific and strangely emotional. Red, because its stars are old and cool. Dead, because no new stars are being born to replace them. It is something like a vast, beautiful, slowly dimming chandelier in an empty ballroom. Still magnificent, still luminous, but no longer being maintained, and destined eventually to go dark. The colour of a galaxy tells you an enormous amount about its history. Blue galaxies are actively forming new stars. The blue light comes from massive, hot, young stars, O-type and B-type stars that burn their fuel at a furious rate and die within a few million years in spectacular supernova explosions. These stars are brief candles, cosmically speaking, but they burn so brightly that even a small number of them can dominate the colour of an entire galaxy. When you see a spiral galaxy glowing with patches of blue and pink in a Hubble photograph, you're seeing stellar nurseries at work. Clouds of gas collapsing under gravity, igniting into new suns, lighting up the surrounding nebulae like lanterns in fog. The Milky Way is still forming stars. Andromeda is still forming stars, though more slowly. The universe, in many places, is still young enough to create. IC1101 is not. Its star-forming gas was consumed or expelled billions of years ago, likely through a combination of processes. Some of the gas was used up in ancient bursts of star formation triggered by galactic mergers, those violent epochs when colliding galaxies compressed their gas reserves and produced millions of new stars in a relatively short time. Some gas was heated to extreme temperatures by the energy released during those mergers, or by jets of radiation from the central supermassive black hole during its active phases. Gas that gets heated above a certain temperature cannot cool down fast enough to collapse into new stars, and it effectively becomes sterilized, still present, still drifting through the galaxy in hot, diffuse wisps, but permanently unable to participate in star formation. And some gas was simply stripped away during interactions with the hot intracluster medium of Abel 2029, a process called Ram pressure stripping, where the galaxy moves through the cluster's hot gas like a swimmer moving through water, and the drag peels gas off its surface. The result is a galaxy populated almost entirely by old stars. The youngest stars in IC1101 are likely billions of years old. The majority are red dwarfs and red giants, stars in the autumn or winter of their lifetimes, glowing with a soft, warm light that gives the galaxy its characteristic amber hue. When you look at IC1101 through a telescope, it does not sparkle or shimmer the way a young spiral galaxy does. It glows, evenly, calmly, like embers in a fireplace that someone forgot to tend. There is no sparkle, no variation, no vivid patches of blue or pink to catch your eye. Just a smooth, warm, amber radiance that fades from bright at the centre to dim at the edges, and the overall impression is one of immense, quiet dignity. A galaxy that has accepted what it is, and is no longer trying to become anything else. There is a warmth to it, but no heat, no urgency, no promise of renewal. It is a galaxy that has finished doing everything it is going to do, and is now simply waiting. For what exactly nobody knows. Perhaps for the last of its stars to burn out, one by one, over trillions of years, until the galaxy is nothing but a vast cloud of cooling stellar remnants, drifting through an even emptier universe. Here is a mainstream historical fact to keep you company in the dark. The idea that galaxies could evolve, that they could change over time, transitioning from one type to another, was not widely accepted until the latter half of the 20th century. For a long time, astronomers treated Hubble's classification system as static. Spirals were spirals, ellipticals were ellipticals, and that was that. It was not until the development of computer simulations in the 1970s and 80s, capable of modelling the gravitational interactions between millions of particles, that researchers could demonstrate convincingly how two spiral galaxies could merge to form an elliptical. The Tumre brothers, Alaa and Juri Tumre, published a landmark paper in 1972 showing how tidal forces during galaxy encounters could produce the kind of tails and bridges observed in interacting galaxies. Their work helped establish the merger paradigm that now underpins our understanding of galaxy evolution. Scholars still argue about the details, how often mergers produce ellipticals versus reformed spirals, how much gas is needed to reignite star formation after a merger, whether some ellipticals formed without major mergers at all, but the broad picture is well established. A quirky fringe detail. Some astronomers have proposed that IC 1101 could, in theory, be revived, brought back to life as a star-forming galaxy, if it were to merge with a sufficiently gas-rich galaxy that dumped fresh fuel into its core. This is not expected to happen anytime soon, since the galaxies remaining in Abel 2029 are mostly gas-poor themselves, having been stripped of their own reserves by the same cluster environment that drained IC 1101. But the theoretical possibility exists. An infusion of cold gas delivered by a wet merger with a gas-rich interloper from outside the cluster could trigger a new round of star formation and briefly turn IC 1101 blue again. It would be like giving a retired marathon runner a shot of adrenaline. Dramatic, temporary, and ultimately doomed to fade. But for a few 100 million years, the largest galaxy in the known universe would blaze with the light of newborn stars, and that image, however hypothetical, is lovely enough to carry into sleep. The colour of IC 1101 is the colour of patience, red and steady and warm. Let it be the colour behind your eyelids as the story continues. You're about to board a photon, the fastest mode of transportation the universe allows, and attempt to cross IC 1101 from one edge to the other. This is a thought experiment, of course, because you are not a photon, and photons do not accept passengers, but your brain is in that lovely half-awake state where anything feels possible. So let us go with it. You step onto the beam of light, feel the instant acceleration, 0 to 300,000 kilometers per second in exactly no time at all, and you begin to move. The first thing you notice is that nothing seems to be happening. You're traveling at the absolute speed limit of the cosmos, faster than anything with mass can ever go. And yet the stars around you barely seem to move. This is because IC 1101 is so enormous that even at light speed, your progress across it is almost imperceptible. Imagine standing on a treadmill in a room so long that the far wall is invisible. You're sprinting, genuinely, maximally sprinting, and the walls on either side are crawling past you with the urgency of continental drift. This is what crossing IC 1101 at the speed of light feels like. The scenery barely changes. The stars around you are old and red and evenly distributed, and they drift past with a patience that borders on contempt for your hurry. You are going as fast as anything can go, and the galaxy could not care less. After 1 year of travel, you have covered 1 light year. That is roughly 9.5 trillion kilometers, a staggering distance by any earthly standard, enough to cross the solar system thousands of times over. But relative to IC 1101, 1 light year is nothing. You have covered roughly 0.002% of the galaxy's diameter. If IC 1101 were a road from London to Moscow, about 2,500 kilometers, you would have moved about 5 centimeters. You would still be in the driveway, you would not have reached the sidewalk. After 100 years, you have crossed 100 light years. This is roughly the distance from Earth to the star Arcturus, one of the brightest stars in our sky. In the context of IC 1101, you have covered about 0.2%. On the London to Moscow road, you are now about 5 meters along. You have reached the front gate. The horizon has not changed. After 1,000 years, a millennium, the span from the Viking Age to today, you have crossed 1,000 light years. That is about 1% of the Milky Way's diameter. Inside IC 1101, it is roughly 0.02%. You are functionally still at the starting line. Civilizations could rise and fall in the time you've been travelling, and IC 101 would not have noticed. After 100,000 years, you have crossed a distance equal to the entire diameter of the Milky Way. One full Milky Way's width, traversed at the speed of light. Inside IC 1101, you're roughly 2% of the way across. 2%, the entire Milky Way, your home galaxy with its hundreds of billions of stars, its spiral arms, its black hole, its planets and moons and asteroids and you, all of it fits into 2% of this thing. Let that settle. It is fine if it does not fully register. Some facts are too large to land all at once. They arrive in installments over the course of a lifetime. After 1 million years, 1 million years of continuous uninterrupted light-speed travel, you are somewhere between 17 and 25% of the way across IC 1101, depending on which diameter estimate you use. On Earth, 1 million years ago, Homo erectus was roaming Africa and Asia, making hand axes and campfires. That entire span of human prehistory converted into light-speed travel gets you roughly a fifth of the way across one galaxy. Here is a mainstream historical fact that pairs well with this thought experiment. In 1867, the Scottish physicist James Clerk Maxwell published his unified theory of electromagnetism, which, among many other achievements, revealed that light was an electromagnetic wave and that it travelled at a finite measurable speed. Before Maxwell, the speed of light was known from measurements, but not understood from theory. Maxwell's equations showed that the speed of light was a fundamental constant of nature, woven into the fabric of electromagnetism itself. This was one of the great intellectual achievements of the 19th century, and it set the stage for Einstein's special relativity 40 years later. Maxwell, brilliant as he was, died of stomach cancer at the age of 48. He would never learn that the speed of light he had so elegantly explained was, in the context of EC 1101, embarrassingly slow. The full crossing takes somewhere between 4 and 6 million years. You have outlived empires, ice ages, and the evolution of every species that has ever existed on Earth, all while sitting on a beam of light that never once slowed down. You reach the far edge of EC 1101 and stop, and you look back, and the edge you departed from is so far away that its light has not yet caught up to you. You are seeing it as it was millions of years ago. The galaxy behind you is a time machine, and you are standing at its output, ancient light still arriving from a departure point that, for all practical purposes, no longer exists in the same state you left it. Researchers still debate how to properly define the edge of IC 1101, since the stellar envelope fades so gradually into the intergalactic background. But regardless of where you draw the line, the journey is longer than human civilization, longer than human evolution, longer than most geological epochs. It is the kind of distance that makes the word distance feel inadequate. Here is a fringe tidbit to close this leg of the journey. Some physicists have speculated about whether shortcuts through space-time, wormholes, Alcubierre drives, exotic geometries permitted by general relativity could theoretically reduce the travel time across structures like IC 1101. The math allows it, barely, under extremely specific conditions that probably cannot be met with any known or foreseeable technology. But the theoretical possibility exists on paper, and it gives science fiction writers just enough rope to work with. For now, though, light speed is the limit, and IC 1101 laughs at it. Let your photon rest. You have earned it, and so have you. Close your eyes, or keep them closed, since they probably drifted shut a while ago, and imagine that you live inside a C1101. Not at its outskirts, not in the sparse periphery where stars thin out like trees at a forest's edge, but deep inside, somewhere in the dense central region where the stellar population is thick and ancient and relentless. What would your night sky look like? What would it feel like to exist inside the largest galaxy anyone has ever found? The first thing you would notice is that there is no true night, not in the way you know it. On Earth, your night sky is dark because stars are incredibly far apart. The nearest star to the Sun, Proxima Centauri, is about 4.2 light-years away, an enormous gulf of emptiness that your brain has trouble appreciating. The vast majority of stars in the Milky Way are so distant and so faint that they are invisible to the naked eye. You can see roughly 5,000 stars on a clear, dark night, which sounds like a lot until you remember that the galaxy contains 200 to 400 billion of them. You're seeing a vanishingly small fraction, and the rest are hidden behind distance, dust, and the limitations of human eyesight. Inside the core of IC 1101, the stellar density is dramatically higher. Elliptical galaxies, particularly their central regions, pack stars much more tightly than the spiral arms of the Milky Way. In the densest parts of IC 1101's core, stars might be separated by fractions of a light year rather than several light years. Your night sky would be ablaze, not with the scattered diamonds on velvet pattern you know from Earth, but with a continuous, dense, warm glow, like looking up into a dome of soft amber light. Individual stars would be difficult to distinguish because there would be so many of them so close together that their light would blur into a luminous haze. Imagine the Milky Way band you see from a dark rural location, that faint river of unresolved starlight. Now imagine that glow covering the entire sky, from horizon to horizon, in every direction. That is a rough approximation of what the sky might look like from deep inside IC 1101. The colour of that glow would be warm. Remember, IC 1101 is dominated by old red stars, red dwarfs and red giants that emit most of their light in the orange and red part of the spectrum. Your sky would not be the blue-white brilliance of a young galaxy, but a deep, rich, amber-gold suffusion, like the light inside a cathedral when the late afternoon sun hits the stained glass. There would be no Milky Way band to trace across the heavens, because there would be no band, just a uniform, omnidirectional radiance, a sky that glows the way a room glows when every lamp is turned on and pointed at the ceiling. You might, on the clearest nights with the sharpest eyes, be able to resolve individual nearby stars as slightly brighter pinpoints against the general haze, the way you can sometimes make out individual streetlights through fog. But the overall impression would be one of immersion, of being inside the light rather than looking up at it from below. It would be beautiful, and it would be constant, and it would mean that the concept of darkness, as you understand it, might never have developed in the culture of any civilization living there. Their mythology, their art, their circadian rhythms, their entire relationship with the cosmos would be shaped by a sky that never fully goes dark. Historians on such a world would never speak of fearing the night, because the night as you know it would not exist. Here is a mainstream historical fact that connects to this imaginary scenario. On Earth, the question of why the night sky is dark is actually a profound cosmological puzzle known as Olbers' paradox, named after the German astronomer Heinrich Olbers, who described it in 1823, though the problem had been noted by others before him. The paradox is this: if the universe is infinite and filled uniformly with stars, then every line of sight from Earth should eventually terminate on the surface of a star, and the entire sky should be as bright as the surface of the sun. The fact that the sky is dark tells us something fundamental. Either the universe is not infinite, or it has not existed forever, or both. The modern resolution involves the finite age of the universe and the expansion of space-time, which means that light from very distant stars has not had time to reach us and is being redshifted out of the visible spectrum. Olbers' paradox delightfully would be even more acute inside EC1101, where the local stellar density is so much higher that the sky really does approach the kind of uniform brightness that Olbers worried about. A quirky fringe tidbit for your drowsy mind. Some astrobiologists have speculated about what kinds of life might evolve in the cores of elliptical galaxies, where radiation levels from nearby stars would be significantly higher than what we experience on Earth. One possibility is that life in such environments might develop much more robust radiation shielding mechanisms, thicker cell walls, more efficient DNA repair enzymes, perhaps even photosynthetic systems tuned to the red-shifted light of ancient stars. Another possibility, less optimistic, is that the radiation environment in the core of a galaxy like IC1101 would be too hostile for complex life to develop at all, making the galaxy a vast luminous desert, trillions of stars and not a single living thing to appreciate them. Scientists still debate the habitability of elliptical galaxies, and the question remains wide open, in part because we have only one example of life to study, and it stubbornly refuses to appear anywhere other than this one small planet orbiting one unremarkable star in one medium-sized spiral galaxy. You lie there, imagining that amber sky. No darkness, no silence, just a warm and omnipresent glow that has been shining since before the Earth existed and will continue shining long after it is gone. It is the sky of a galaxy that has seen everything and forgotten nothing, and it is watching over you the way a very old and very patient light watches over a very small and very temporary room. Breathe into it. The amber does not mind. It is easy to throw around the word largest without giving it proper context, so let us now take IC1101 and stand it next to the other galaxies that humanity has, at various points, considered impressively large, and watch them all shrink. This is the part of the story where the supporting cast walks on stage and immediately realizes they have been catastrophically miscast. You have been using the Milky Way as your ruler, and that ruler has served you well. But now it is time to see what happens when other galaxies try to stand next to IC1101, and the answer, in every case, is the same. They look adorable. Start with Andromeda, the Milky Way's nearest large neighbour and the galaxy most people picture when they hear the word galaxy. Andromeda is a beautiful barred spiral, roughly 220,000 light-years in diameter, about twice the width of the Milky Way depending on how you measure. It contains approximately 1 trillion stars. Andromeda is big enough that you can see it with the naked eye from a dark site, a faint smudge in the constellation that shares its name. For centuries it was the poster child for galactic grandeur. Next to IC1101, Andromeda is a pond next to an ocean. IC1101 is roughly 25 times wider than Andromeda, and contains roughly 100 times as many stars. You could lose Andromeda inside IC 1101, the way you lose a contact lens on a gymnasium floor. Theoretically, it is in there somewhere, but good luck finding it. Now consider M87, the giant elliptical galaxy at the centre of the Virgo cluster, about 53 million light-years from Earth. M87 is famous for two things: its spectacular relativistic jet, a beam of plasma shooting out from its central black hole at nearly the speed of light, extending thousands of light-years into intergalactic space, and for being the galaxy whose black hole was imaged by the Event Horizon Telescope in 2019, producing that iconic glowing orange donut photograph that went viral. M87 is a genuinely enormous galaxy, roughly 240,000 light-years across, with a mass of several trillion suns. It is the dominant galaxy in its cluster, a CD galaxy in its own right, and it has clearly consumed many smaller galaxies over its lifetime. Yet a C1101 is roughly 20 times wider than M87 and likely several times more massive. M87, which seemed like the boss of its galaxy cluster, is middle management compared to IC1101. What about the Milky Way and Andromeda after they merge? Remember Milkomeda, that hypothetical future galaxy born from the collision expected in 4 to 5 billion years? Milkomeda will be an elliptical galaxy containing perhaps 1.5 trillion stars with a diameter that might reach 300 to 400,000 light-years once the merger debris settles. Impressive by local standards, certainly. A far cry from IC1101. Milkomeda would fit inside IC1101 more than a dozen times over in terms of diameter alone, and the volume comparison is even more humiliating. The most dramatic event in our local cosmic future will produce a galaxy that is still a fraction of what IC1101 already is. Here is a mainstream historical fact woven into this gallery of giants. The first systematic attempt to measure the sizes of galaxies beyond the Milky Way came in the 1920s and 30s, as astronomers like Hubble, Milton Humason, and others used Cepheid variables in the redshift distance relationship to estimate how far away galaxies were, and therefore how physically large they must be. These early measurements were often wildly inaccurate. Hubble's original estimate of the distance to Andromeda was off by more than a factor of 2, which meant his size estimates were correspondingly wrong. The field spent decades refining its distance ladder, correcting errors, and recalibrating. It is a humbling reminder that the numbers we cite today are themselves the product of generations of incremental improvement, and future astronomers may look back at our measurements of IC1101 with the same mixture of respect and gentle amusement that we direct at Hubble's early work. A fringe tidbit for your collection: there are a few other galaxies that have occasionally been cited as rivals to IC1101 in size. One is the radio galaxy Alcyonius, discovered in 2022, which has enormous radio lobes, jets of plasma extending from its central black hole, spanning roughly 16 million light-years. However, those lobes are not the galaxy itself. They are outflows from the black hole that extend far beyond the stellar body. The galaxy proper is much smaller. Another contender is Hercules A, another radio galaxy with spectacular jets, and there are various brightest cluster galaxies scattered across the universe that approach IC1101 scale. Researchers still argue about which galaxy truly holds the largest title, because the answer depends on exactly what you measure: stellar body, extended halo, radio lobes, dark matter halo, and how you define the boundary. But by the most commonly used metric, the extent of the stellar envelope, IC1101 remains at or near the top, the undisputed heavyweight champion of the galactic weight class. And then there are the galaxies you have never heard of. the ones hiding in the deep field images of the Hubble and James Webb space telescopes, thousands of them in a single frame, each one an island of stars with its own history of mergers and star formation and quiet aging. Some of them are large, some are small, most are utterly unremarkable by cosmic standards, middleweight spirals and compact ellipticals doing their thing in the background of the universe. And somewhere in that background, in a cluster you might not notice, unless you were specifically looking for it, sits IC1101, quietly being larger than all of them, a cathedral surrounded by dollhouses exactly as promised. Scholars still debate whether the largest galaxy title carries any deep physical significance, or whether it is simply an accident of merger history, the cosmic equivalent of asking who is the tallest person in the room. The tallest person is not necessarily the most interesting person, but they are certainly the hardest to ignore. Let the comparisons fade. You have the scale now. It lives somewhere behind your eyes, in the place where your brain stores facts too large for regular filing. Let it sit there, warm and oversized, while the story moves on. You have spent a long time now looking at IC1101, and it is time to step back and look at the kingdom it rules. Abel 2029 is not just a backdrop or a setting, it is a character in this story, a vast gravitational machine that created the conditions for IC1101 to become what it is, and that continues to shape it today. Without the cluster, the monster at its centre would be just another large galaxy. With the cluster, it is the largest structure of its kind that human eyes have ever measured. Abel 2029 spans roughly 20 to 30 million light-years across, depending on where you draw the boundary, and contains somewhere in the range of several thousand galaxies. That number is not as precise as you might hope, because counting galaxies in a cluster is like counting fish in a murky pond. You can see the big ones clearly, but the small faint ones blend into the background, and there is always the question of which fish actually belong to this pond and which are just passing through. The cluster's total mass, including galaxies, intra-cluster gas and dark matter, is estimated at roughly 100 trillion solar masses, roughly 100 times the mass of the Milky Way. Most of that mass is dark matter, the invisible substance that you will meet properly in the next section, but the visible components are dramatic enough on their own. The intracluster medium, that superheated gas filling the space between galaxies, is one of the most extreme physical environments in the universe. In Abel 2029, this gas has been measured at temperatures exceeding 70 million degrees Kelvin, which is several times hotter than the core of the Sun. At these temperatures, the gas is fully ionized, atoms stripped of their electrons creating a plasma that radiates fiercely in X-rays. The Chandra X-ray Observatory has produced stunning images of this gas, revealing a smooth, symmetric glow centered on IC1101. The smoothness tells astronomers that Abel 2029 is a relaxed cluster, meaning it has not experienced a major disruption, like a collision with another galaxy cluster, in a very long time. It is an old, settled system, and the calm at its centre has allowed a C1101 to grow undisturbed for billions of years, steadily accreting mass and starlight like a spider at the centre of a very patient web. Here is a mainstream historical fact that connects to the science of galaxy clusters. The idea that X-rays could reveal the hot gas between galaxies was first confirmed in the early 1970s when the Uhuru satellite, the first satellite dedicated to X-ray astronomy, launched by NASA in 1970 from a platform off the coast of Kenya, detected X-ray emission from several galaxy clusters. Uhuru, whose name means freedom in Swahili and was chosen in honour of the launch coinciding with Kenyan Independence Day, opened an entirely new window on the universe. Before Uhuru, astronomers knew that galaxy clusters existed, but they had no way to see the vast reservoirs of hot gas that pervade them. The discovery revealed that galaxy clusters were not just collections of galaxies floating in empty space, but complex physical systems with enormous reservoirs of matter between the galaxies themselves. It was like discovering that the air in a room was actually made of something interesting, and that the something interesting weighed more than the furniture. Gravitational lensing, which you encountered briefly a few sections ago, plays a particularly elegant role in the study of Abel 2029. The cluster's immense mass curves the space-time around it, bending the paths of light from more distant galaxies behind it. This bending produces distorted images, arcs, rings, and duplicated copies of the background galaxies, and the degree of distortion tells astronomers how much mass is doing the bending and where that mass is concentrated. Researchers have used this technique to map the dark matter distribution in Abel 2029 with remarkable precision, and the results show a massive concentrated dark matter, halo-centered almost exactly on IC1101. The galaxy and the dark matter are locked in a gravitational embrace, each one shaping the other. Scientists still debate the exact profile of this dark matter halo, whether it is cuspy, with a sharp density spike at the center, or chord, with a flatter central region, because the two profiles lead to different predictions about how the galaxy formed and how it will evolve. A quirky fringe detail: some of the galaxies in Abel 2029 are moving at speeds of over 1,000 kilometers per second relative to the cluster's center of mass. At those speeds, the intergalactic gas acts almost like a wind, stripping gas from the galaxies as they plow through it. This process, ram pressure stripping, can fundamentally alter a galaxy's evolution, removing the gas it needs to form new stars and transforming it from a vibrant spiral into a quenched, passive object. In a sense, the cluster environment is sterilizing its members, and IC1101, sitting calmly at the center while smaller galaxies are buffeted and stripped of their resources, is the ultimate beneficiary of this process. It is not just eating galaxies, it is profiting from their degradation, like a landlord who collects rent while the building slowly decays around the tenants. The stripped galaxies, drained of gas and robbed of their capacity for renewal, become ghost galaxies, elliptical husks orbiting the cluster center, their best years behind them, their stars slowly aging with no replacements forthcoming. Some of these ghost galaxies will eventually fall all the way into IC1101 and be absorbed entirely, their identities erased, their stars mixed into the vast communal glow of the central giant. It is, in a way, the ultimate form of recycling. Nothing is wasted, everything is reused, but the original is lost forever. The comparison is not flattering, but then, IC1101 has never needed to be liked. It only needs to be massive, and in that regard it has succeeded beyond any reasonable expectation. Let the cluster recede from your imagination now. You've seen its hot gas, felt its gravity, watched its galaxies spiral slowly inward. The kingdom makes sense. The king on its throne makes sense. And you, lying here in the dark, are the furthest thing from a galaxy cluster, and that is exactly why you can appreciate one. Small things are the best observers of large things. That is not a scientific fact. It is just something that feels true tonight. There is something hiding inside IC1101 that you cannot see, cannot touch, cannot taste, cannot smell, and cannot detect with any of the instruments sitting on your bedside table, which, admittedly, are limited to a phone and maybe a glass of water. But even the most sophisticated instruments humanity has ever built cannot directly detect this substance. It is called dark matter, and it makes up the vast majority of IC 1101's total mass. You have been admiring the visible galaxy, the stars, the gas, the central black hole. But all of that, everything you have learned about so far, accounts for only a small fraction of what IC 1101 actually is. The rest is dark, and the dark part is what holds everything together. Dark matter is one of the most profound and frustrating mysteries in modern physics. We know it exists because we can see its gravitational effect everywhere we look. Galaxies rotate too fast for the amount of visible matter they contain. Without some additional, unseen mass providing extra gravity, their outer stars would fly off into space like water droplets from a spinning wheel. Galaxy clusters contain far more mass than the combined mass of their visible galaxies and gas. We know this from gravitational lensing measurements and from the temperature of the intra-cluster gas, which would not be as hot as it is unless it were being squeezed by the gravity of something much more massive than what we can see. And the large-scale structure of the universe, the vast cosmic web of filaments and voids that galaxies are organised into, requires dark matter to have formed in the way it did. Without dark matter, the universe as we observe it does not make sense. And yet, despite decades of searching, nobody has directly detected a dark matter particle. We know what it does. We do not know what it is. The story of dark matter's discovery is one of the most fascinating in all of physics. In 1933, the Swiss astronomer Fritz Zwicky, a brilliant, combative, and by all accounts somewhat difficult personality, was studying the Coma Cluster, a galaxy cluster about 320 million light-years from Earth. He measured the velocities of the galaxies within the cluster and applied a standard physics technique called the virial theorem to estimate the cluster's total mass. The results stunned him. The cluster appeared to contain roughly 400 times more mass than could be accounted for by its visible galaxies. Zwicky called this missing substance dunkle Materie, dark matter, and published his findings. The scientific community largely ignored him for nearly 4 decades, partly because the instruments of the era could not confirm his result, and partly because, frankly, Zwicky had a reputation for being abrasive. He once called his colleagues spherical bastards, explaining that they were bastards no matter which way you looked at them. Historians still argue about whether Zwicky's difficult personality contributed to the delay in accepting his discovery, or whether the evidence simply was not strong enough at the time to overcome the extraordinary nature of the claim. The confirmation came in the 1970s, when astronomer Vera Rubin and instrument maker Kent Ford measured the rotation curves of spiral galaxies with unprecedented precision. They found that stars at the outer edges of galaxies were orbiting just as fast as stars near the centre, a result that flatly contradicted the expectation that orbital speed should decrease with distance from the centre, just as outer planets orbit the Sun more slowly than inner ones. The only explanation was that the galaxies were embedded in massive invisible halos of dark matter that extended far beyond the visible stars. Rubin's work was meticulous, her data irrefutable, and it transformed dark matter from Zwicky's lonely hypothesis into a cornerstone of modern cosmology. Rubin was widely considered deserving of the Nobel Prize, though she never received one before her death in 2016, a fact that continues to generate debate in the physics community. The confirmation transformed cosmology. Within a few years, dark matter went from a fringe hypothesis to a foundational element of the standard cosmological model. Today, we estimate that dark matter constitutes roughly 27% of the total mass-energy content of the universe, about 5 times more than all the ordinary matter, atoms, molecules, stars, planets, people, combined. You are, in a very real sense, the minority substance. Most of what exists is dark, and the bright, tangible world you experience, sunlight, solid ground, the warmth of another person's hand, is an exception, a thin frosting on a cake made mostly of something invisible that is either deeply unsettling or strangely comforting, depending on how close you are to sleep. IC1101 sits inside a dark matter halo that is almost incomprehensibly massive. The total mass of Abel 2029, most of which is dark matter, is estimated at roughly 100 trillion solar masses, and a significant fraction of the dark matter is concentrated around IC1101 at the cluster's centre. The dark matter halo shapes the galaxy the way a skeleton shapes a body. You cannot see it from the outside, but without it the structure collapses. The stars, the gas, the black hole, all of them are embedded in the dark matter's gravitational field, orbiting within it, supported by it, sculpted by it. Without the dark matter halo, the stars in IC1101 would fly apart. There simply is not enough visible mass to hold such an enormous structure together. The dark matter is not decoration. It is the foundation. It is the invisible floor that every visible object in the galaxy is standing on, and if you removed it, the entire structure would dissolve like sugar in hot water, scattering 100 trillion stars into the void. A quirky fringe detail to take into your dreams. Some physicists have proposed that dark matter particles might occasionally annihilate each other when they collide, producing detectable gamma rays. If this is true, then the densest regions of dark matter, like the core of the halo surrounding EC1101, might be faintly glowing in gamma rays, a ghostly luminescence from a substance that is otherwise invisible. Researchers have looked for this signal with gamma-ray telescopes like Fermi, but so far the results are inconclusive. Scholars still debate whether the signal is there but too faint to detect, or whether dark matter simply does not annihilate in the way the models predict. Either way, the image is haunting. A vast, invisible ocean of matter, possibly shimmering with the faintest imaginable light, holding together the largest galaxy anyone has ever found. You're surrounded by things you cannot see, and they are holding you together too. Gravity, air, the warmth of your blanket. The dark is not empty. It never was. The universe is getting bigger. Right now, as you lie here, the fabric of space-time itself is stretching, and every galaxy that is not gravitationally bound to your local group is moving away from you, not because the galaxies are flying through space, but because the space between them is expanding, like dots painted on the surface of a balloon that someone is slowly inflating. This expansion was discovered in 1929 by Edwin Hubble, who noticed that distant galaxies were redshifted, their light stretched to longer wavelengths, in a way that was proportional to their distance. The farther away a galaxy was, the faster it appeared to be receding. This was the first observational evidence that the universe was not static but expanding, and it shattered the prevailing cosmological model so thoroughly that even Einstein, who had introduced a cosmological constant to keep his equations compatible with a static universe, reportedly called it his greatest blunder. The expansion of the universe raises a haunting question about IC1101. What happens to the largest galaxy in the cosmos when the cosmos itself is pulling everything apart? The answer is nuanced, and it depends on the timescale you're thinking about. In the very short term, nothing changes. IC1101 is gravitationally bound to its cluster, held together by forces far stronger than the gentle tug of cosmic expansion. But in the very long term, the story becomes more complicated and considerably more melancholy, and you should probably get comfortable, because the future of the universe is not a cheerful topic, though it is a beautiful one in the way that sunsets are beautiful, glorious precisely because they end. In the short term, By cosmic standards, meaning the next few billion years, IC1101 will probably keep growing. It is still at the centre of Abel 2029, still at the bottom of the deepest gravitational well in its local region, and there are still galaxies slowly spiralling inward through dynamical friction. Each one that reaches the centre will be absorbed, adding its mass to IC1101's already bloated frame. The cluster itself is gravitationally bound, meaning the expansion of the universe cannot tear it apart. The galaxies within Abel 2029 are close enough and massive enough that their mutual gravity overcomes the cosmic expansion, keeping them locked together in the same way that the Milky Way and Andromeda are gravitationally bound despite the universe's expansion, and will merge regardless. But in the long term, tens of billions of years, hundreds of billions of years, beyond the horizon of any reasonable prediction, the story gets darker. In 1998, two independent teams of astronomers made a discovery that shook cosmology to its core. The expansion of the universe is accelerating. Not just expanding, accelerating. Something is pushing space-time apart faster and faster, and that something has been given the name dark energy, which is an honest admission that we have no idea what it is. Dark energy constitutes roughly 68% of the total energy content of the universe, making it the dominant component of everything that exists, and we understand it less well than almost anything else in physics. Scholars still debate whether dark energy is a true cosmological constant, a fixed property of space-time itself, or a dynamic field that changes over time, and the answer has profound implications for the ultimate fate of the universe. If dark energy is constant and the acceleration continues, then over sufficiently long timescales, the universe will enter what cosmologists call the Big Freeze or heat death, a state of maximum entropy where all stars have burned out, all black holes have evaporated through Hawking radiation, and the universe is a cold, dark, empty void expanding forever. In this scenario, IC1101 will eventually exhaust its stellar fuel. Its last remaining red dwarfs, those stubborn little stars that burn so slowly they can last for trillions of years, will finally flicker out, one by one, over a timescale so long that the current age of the universe is a rounding error. What remains will be a vast collection of stellar remnants, white dwarfs cooling to black dwarfs, neutron stars slowly spinning down, and the supermassive black hole at the centre, which will be the last thing to go. Black holes evaporate through Hawking radiation, but the process is fantastically slow. A black hole with the mass of IC1101's central monster would take something on the order of 10 to the power of 100 years to evaporate. A number so large that writing it out in full would take more space than this entire script. Here is a historical fact that grounds the abstraction. The discovery of the accelerating expansion was made by studying Type 1, a supernova, exploding white dwarf stars that serve as standard candles, because they all reach approximately the same peak brightness. By measuring how bright these supernovae appeared versus how bright they should have been based on their redshift, astronomers Saul Perlmutter, Brian Schmidt and Adam Rees showed that distant supernovae were fainter than expected, meaning they were farther away than a decelerating universe would predict. The discovery won all three the Nobel Prize in Physics in 2011 and remains one of the most important observations in the history of cosmology. A fringe tidbit for the edges of your awareness. Some speculative models of dark energy predict a scenario called the Big Rip, in which the acceleration increases so dramatically over time that it eventually overcomes all forces: gravity, electromagnetism, even the nuclear forces holding atoms together. In a Big Rip scenario, galaxy clusters would be torn apart first, then individual galaxies, then solar systems, then planets, then atoms themselves. IC 1101, for all its mass and gravitational dominance, would be shredded like tissue paper. Most cosmologists consider the Big Rip unlikely given current data, but it has not been conclusively ruled out, and the possibility lingers in the literature like an uninvited guest who refuses to leave. The data currently favours a gentler fate, the slow, cold, quiet fade of the Big Freeze, but the universe has surprised us before, and it would be unwise to assume it has finished surprising us now. Sleep well. The future of IC 1101, like the future of everything, is uncertain, but tonight it is still there, 100 trillion stars glowing softly in the dark, held together by gravity and dark matter, expanding or not, dying or not, existing in the present tense for as long as there is a present tense to exist in, and you are here too in your own present tense, which is warm and quiet and enough. You have been calling IC 1101 the largest galaxy ever found, and that claim deserves one last honest examination before you carry it into sleep, because science is not in the business of absolutes, and the universe has a well-documented habit of hiding things larger than whatever we just call the largest. So let us ask the uncomfortable question: could there be something out there even bigger than IC 1101? And if so, why have we not found it? The first thing to understand is that we can only see a portion of the universe. The observable universe has a radius of about 46.5 billion light-years, determined by the age of the cosmos and the expansion of space-time since the Big Bang. Light from objects beyond this horizon has not had time to reach us, no matter how powerful our telescopes are. This means that the observable universe is a sphere centered on Earth, not because Earth is special, but because every observer sees their own sphere, limited by the speed of light and the age of everything. Beyond that sphere, the universe almost certainly continues, possibly infinitely, and it likely contains galaxies and galaxy clusters and structures of every size. There could be a galaxy out there, beyond our cosmic horizon, that makes IC 1101 look like a toy. We would never know. We could never know, at least not with current physics. It is the ultimate there might be a bigger fish scenario, and it is maddening in the best possible way. The observable universe, for all its enormity, 93 billion light-years in diameter, containing trillions of galaxies, might be a tiny bubble in a much grander structure, and every superlative we attach to objects within it is provisional, qualified by the caveat that we are only looking at a fraction of what is out there. It is the cosmic equivalent of declaring yourself the tallest person in the room when you do not know how many rooms the building has. Within the observable universe, there are a few structures that have challenged IC 1101's claim, at least in certain categories. You've already met Alcyonius, the giant radio galaxy discovered in 2022, whose radio lobes span roughly 16.3 million light-years, far larger than IC 1101's stellar body. But those lobes are not the galaxy itself. They are jets of relativistic plasma launched from the central black hole, extending vast distances into the intergalactic medium. The stellar body of Alcyonius is relatively modest. It is like saying that a garden hose is 20 meters long because the water spray reaches that far. Technically, the system extends that distance, but the hose itself is much shorter. Still, Alcyonius reminded astronomers that largest depends entirely on what you measure. There are also the brightest cluster galaxies scattered across the sky, central galaxies and other massive clusters that share IC 1101's position and likely formation history. Some of these, like the central galaxy and the Phoenix cluster, are actively forming stars at extraordinary rates, hundreds or even thousands of solar masses per year, and are still growing their stellar populations. Others, like the central galaxy in Abel 2261, have unusually large and diffuse cores that hint at complex merger histories, and possibly even recoiling supermassive black holes knocked from the centre by gravitational wave kicks. Researchers still debate which of these brightest cluster galaxies is truly the most massive and most extended. Different studies using different wavelengths and different techniques produce different rankings, and the leaderboard shifts with each new publication. Here is a mainstream historical fact to keep the story human. The first deep field image, a photograph that revealed thousands of galaxies in a tiny, seemingly empty patch of sky, was the Hubble Deep Field, taken in 1995 over 10 consecutive days of exposure time. The director of the Space Telescope Science Institute, Robert Williams, made the controversial decision to devote a significant portion of Hubble's valuable observing time to staring at what appeared to be a blank area of sky near the Big Dipper. Many astronomers thought it was a waste of time. The resulting image contained over 3,000 galaxies in a patch of sky roughly the size of a grain of sand held at arm's length, and it fundamentally changed humanity's understanding of the scale and richness of the universe. Every subsequent deep field image, the Hubble Ultra Deep Field, the JWST Deep Fields, has only deepened that revelation. And somewhere in the background of those images, there may be galaxies we have not yet properly measured that rival or exceed IC1101 in size. A quirky fringe tidbit for your fading wakefulness. Some cosmologists have proposed the existence of truly enormous structures that would dwarf anything we've found so far, hypothetical objects called supervoids and superclusters that challenge the cosmological principle, the assumption that the universe is roughly the same everywhere at the larger scales. The Hercules Corona Borealis Great Wall, for instance, is a gamma-ray burst structure roughly 10 billion light-years across that, if real, would be the largest known structure in the observable universe, far larger than any galaxy cluster or supercluster. But this is a large-scale matter distribution, not a galaxy. The distinction matters, because a galaxy is a self-contained gravitational system with a defined identity, while the Great Wall is more like a pattern in the wallpaper, real, but not an object in the same sense. Scholars still debate whether structures this large are genuine physical entities or statistical artifacts created by the way we sample the sky. The honest answer to could something bigger exist is almost certainly yes. The universe is too vast, too varied, and too incompletely surveyed for IC1101 to be the absolute limit. But what makes IC1101 special is not just its size, it is the fact that we've measured it, studied it, and grappled with its implications in enough detail to understand what it tells us about galaxy formation, dark matter, cosmic expansion, and the limits of gravitational assembly. It is not just a record holder, it is a laboratory. And laboratories do not need to be the biggest thing in the world to be the most important. The question is dissolving now the way questions do when you're almost asleep. Is there something bigger? Maybe. Probably. Does it matter right now? No. Right now there is IC1101 and there is you. And the gap between those two things is exactly the right size for a good night's rest. Something has been happening to you over the course of this story, and you might not have noticed it because it happened slowly, the way a sunrise happens, so gradually that you cannot point to the exact moment the sky changed colour, but suddenly you realise you're standing in light. What has happened is this. You've been shrinking, not physically. Your body's exactly the same size it was when you pressed play, but your sense of self, your ego, your unconscious assumption that you and your world are significant in the grand scheme of things, that has been gently, steadily reduced, and it has been replaced by something that feels surprisingly good. It feels like relief. This feeling has a name, or at least an approximation of one. Astronauts call it the overview effect, the cognitive shift that occurs when you see the Earth from space for the first time and suddenly realize, viscerally and emotionally, that the planet is small, that borders are invisible, that everything you have ever worried about is happening on a pale blue marble, suspended in a void so vast that the marble itself is barely visible. Edgar Mitchell, the Apollo 14 astronaut, described it as an explosion of awareness. He said he looked at Earth from the moon and experienced a sense of connectedness so profound that it changed the rest of his life. Many astronauts report similar experiences. Tears, silence, a feeling of overwhelming peace mixed with sadness at the fragility of the planet. You have not been to space tonight, but IC 1101 has given you something similar. It has shown you a galaxy so large that the Earth is not even a rounding error inside it. It is a subatomic particle, a single electron in a mountain of iron. The Milky Way, your entire galaxy, is a crumb on IC 1101's table, and IC 1101 itself, for all its enormity, is one galaxy among trillions in an observable universe that may itself be a vanishingly small fraction of the full cosmos. The chain of smallness goes on and on and on, and at the bottom of it, so tiny as to be essentially non-existent on any cosmic scale, is you. A warm, breathing, slightly sleepy collection of atoms lying in a bed on the surface of a small planet, somehow aware of all of this, and somehow still here. Here is a mainstream historical fact that captures this feeling with surprising precision. In 1990, the Voyager 1 spacecraft, then roughly 6 billion kilometers from Earth, turned its camera back toward the inner solar system and took a photograph. In that photograph, Earth appears as a tiny dot, less than a single pixel wide, suspended in a sunbeam. Carl Sagan, the astronomer and science communicator, wrote about that image with the eloquence that has never been surpassed. Look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was lived out their lives. Sagan's point was not that we are insignificant, it was that our significance is self-generated, that it comes from within, from the fact that we are the universe's way of looking at itself, and that this fact alone is worth protecting. IC 1101 does not know it is large. You know it is large. That difference is everything. There is a scholarly debate embedded in this philosophical terrain that is worth mentioning as you drift. Some philosophers of science argue that the Copernican principle, the idea that Earth and humanity occupy no special position in the cosmos, should make us humble but not nihilistic. Others argue that the sheer improbability of conscious, self-aware life, arising from a universe of mostly hydrogen and gravity, means that we are in fact cosmically extraordinary, not despite our smallness but because of it. The fact that atoms can arrange themselves into a pattern complex enough to contemplate IC 1101 is, by any reasonable measure, as remarkable as IC 1101 itself. Scholars still debate where the balance lies between cosmic humility and cosmic self-congratulation, and honestly, both positions feel right depending on whether you have had your coffee yet. There is a Japanese concept called mono no aware, which translates roughly to the pathos of things, a gentle sadness at the transience of beauty, the awareness that everything beautiful is beautiful partly because it will not last. Cherry blossoms are lovely because they fall, sunsets are stunning because they end, and perhaps IC1101, for all its incomprehensible age and scale, is subject to the same principle. It will not last forever. Its stars will die. Its black hole will evaporate. The cluster will disperse. Even the largest thing we've ever found is temporary, and there is something deeply, quietly beautiful about that. You are temporary too, on a much shorter timescale, and the fact that you are using some of your limited, precious, never-to-be-repeated hours of consciousness to learn about a galaxy you will never visit is an act of pure, unnecessary wonder. The kind of thing that makes being alive feel like a privilege rather than an accident. The universe did not have to produce creatures that find it interesting, but it did. And here you are, interested. A quirky fringe tidbit for the very last shreds of your waking mind. Some researchers in the field of astrobiology have proposed a concept called the cosmic zoo hypothesis, which suggests that advanced extraterrestrial civilizations might be aware of us, but have chosen not to make contact, observing us the way we observe animals in a nature reserve, from a distance, without interference, waiting to see what we do next. If such civilizations exist, and if some of them reside in galaxies as large as IC1101, then they would have had billions of years more than us to develop, and their perspective on the cosmos would make ours look like a child's first day at school. The hypothesis is untestable and probably unfalsifiable, which makes it fringe by any reasonable definition, but it is a lovely thing to think about as you fall asleep. The idea that somewhere, in a galaxy that dwarfs imagination, someone might be watching this little planet with patient curiosity, the same way you watch stars from your bedroom window. IC1101 does not care about you. The universe does not care about you, but you care about you and you care about IC1101, and that caring is a kind of light, small, warm, and unbelievably improbable. Carry it gently. You're almost home. You've travelled a very long way tonight. You started in your bed, and then you were not in your bed anymore. You were standing at the edge of the observable universe, looking at something so large that language bent under the weight of trying to describe it. IC1101, a galaxy 4 to 6 million light-years across, 100 trillion stars, a supermassive black hole that could swallow solar systems the way you swallow water, a gravitational empire built over billions of years by consuming everything that wandered too close. You held all of that in your mind, and you are still here, and your pillow is still soft and the room is still quiet, and that is a small miracle in itself. What does IC1101 teach us? It teaches us that the universe builds on scales that have nothing to do with human experience. We measure our lives in decades, our history in millennia, our geology in millions of years, and IC1101 laughs at all of it gently, the way an ocean laughs at a teacup. It teaches us that growth at the cosmic level is patient and relentless, that gravity never stops working, that mergers never stop happening, that the universe is always under construction even when it looks perfectly still. It teaches us that the largest things are often the quietest. IC1101 is not exploding. It is not collapsing. It is not doing anything dramatic at all. It is just sitting there at the center of its cluster, glowing with the soft red light of 100 trillion aging stars, and existing with a calm that you might envy if you let yourself. And it teaches us something about limits, or rather, about the absence of them. Every time humanity thought it had found the edge of the universe, the edge moved. Every time we thought we understood the scale of things, the scale got bigger. The ancient Greeks thought the cosmos was a set of nested crystalline spheres surrounding the Earth. Copernicus pushed the Earth off its throne. Galileo revealed the Milky Way as a river of individual stars. Hubble proved there were galaxies beyond the Milky Way. And then someone measured IC 1101, and the idea of large had to be renegotiated entirely. Historians of astronomy sometimes speak of great humiliations, moments when humanity's self-image was forcibly downsized by a new discovery. IC 1101 is not usually listed among them, but perhaps it should be, because there is something uniquely humbling about discovering not just that the universe is vast, but that it contains individual objects that are, by themselves, vaster than your imagination can comfortably hold. And yet, and this is the part that might follow you into your dreams, the universe also builds small. It builds atoms and molecules and cells and organisms, and eventually it builds creatures capable of lying in a dark room and wondering about galaxies they will never visit. The same physics that assembled EC 1101 assembled you. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force. 4 interactions, and from them, everything. The galaxy and the listener are branches of the same tree, grown in different directions at different scales, but rooted in the same soil. That is not poetry, that is physics, and the fact that physics can sound like poetry is one of the better arguments for paying attention in science class. Or, failing that, for listening to bedtime stories about galaxies at unreasonable hours of the night. Here is one last scholarly debate to carry into the dark. Cosmologists still argue about whether the universe is infinite. If it is, if space-time extends forever in every direction, with galaxies and clusters and voids repeating without end, then IC 1101 is not even particularly special. In an infinite universe, there would be infinitely many galaxies of every possible size, including many larger than IC 1101, scattered across distances so great that they are beyond any possible observation. The largest galaxy we have ever found would be, in the grander scheme, utterly ordinary. That thought should either terrify you or comfort you, and the fact that you get to choose which one it does is proof that you are the most interesting object in this story. Not because you're the largest, but because you are the only one that is listening. A final fringe tidbit, and then you rest. Some theoretical physicists have entertained the notion that our entire observable universe might itself be a kind of structure embedded within a much larger multiverse, a collection of universes, each with different physical constants, different histories, different versions of everything. If the multiverse is real, then IC 1101 is not only small compared to the universe, it is incomprehensibly small compared to the totality of existence. But this is speculation at the very frontier of physics, the place where mathematics meets imagination, and neither one is sure who is leading. It is the kind of thought that is perfectly suited for the boundary between waking and sleeping, where the rules get soft and the impossible starts to feel like a reasonable suggestion. You've done something remarkable tonight. You've held a galaxy in your mind. Not a small one, not an easy one, but the largest one humanity has ever measured. You've felt its mass and its silence and its ancient amber light. You have travelled across it at the speed of light and still been too slow. You have imagined its sky, counted its stars, met its black hole, watched it eat its neighbours, and learned its name. IC 1101. Remember it, or don't. It'll still be there either way, burning quietly, a billion light years from your eyelids, in a universe that has no obligation to make sense but occasionally does anyway. And now the story is ending the way all good stories end, not with a bang, not with a twist, but with a slow, deliberate softening, like a hand easing off a piano key and letting the last note fade into the room. Your breathing is slow. Your thoughts are thin and warm. moving like silk ribbons in still air. The stars of IC1101 are behind you now, all 100 trillion of them, each one a tiny furnace burning hydrogen into helium, into carbon, into iron, the same elements that built your bones and your blood and the pillow under your head. You're made of the same stuff as the largest galaxy in the known universe, arranged into a much smaller and much more interesting shape. The atoms in your body were forged in stars that died before the Earth existed, and one day, in the very far future, those atoms will be part of something else. A rock, a cloud, a new star, a new story. Nothing is wasted, nothing is lost. It is all just rearranged over and over on timescales that make even IC1101 seem brief. So let go. Let the galaxy hold you. Let the warm red light of 100 trillion ancient suns wash over your closed eyelids, and feel yourself dissolve, gently, gratefully, into the softest part of the night, your stardust. You have always been stardust, and stardust, when it is tired, sleeps. So sleep, sleep well, and dream of something enormous.